Okay, I'll start recording. Okay, yeah, so the first speaker, let me just introduce the speaker. So the first speaker is Siva Hari, who is a senior research scientist in the computer architecture group at NVidia, and his current research focuses on all things resiliency and reliability related, with a particular focus on making GPUs resilient through architecture and software level solutions, and he got his PhD from UIUC. And today he's going to talk to us about resilience and safety for autonomous vehicles. So with that, Shiva.
All right, thank you. Let me share. Okay. All right. Can you see the slides and hear me okay?
Yeah.
Perfect. Okay. So thank you for the introduction. I'll be giving you an overview about some of the work we have done and give a broad overview about the topics in the autonomous safety systems and also some of the touch upon the resilience topics. To start at a very high level, autonomous vehicles are gaining attention. There has been a lot of advancements being made. I was looking at some of the recent information. The survey says that as of May 2018, more than 93% of new vehicles that are shipped in the US or that are sold in the US include at least one ADAS feature, or the advanced driver assistance features. These include adaptive cruise control, blind spot detection. Many of you probably have in your cars these kind of features. What's more interesting is that in California itself, 61 companies hold permits to test AVs with the drivers. And that's like incredible number. And there are 5 companies that hold permits to test AVs without a driver. And a lot of these advancements are being made due to, again, advancements in sensor technology, advancements in the algorithms, the processing of the sensor data, the platforms that provide the compute capabilities to execute all of that in the real-time environment, and simulation technology that is needed to develop, design, and test a lot of these systems. So the picture on the right is essentially showing that we have an AV with many types of sensors attached to a rig on top of this particular vehicle there. It's used for sensing. And at the bottom there's a picture of NVIDIA Drive Pegasus platform that provides enough capability to do a lot of these sensing. And the picture on the right is essentially showing a simulation framework. So in short, a simplistic view of an autonomous vehicle, it can be as simple as this. Like an autonomous vehicle system senses the world around it using a bunch of sensors. It gets the data from those sensors, performs the perception and the localization, localizes the vehicle itself in what it sees around it as the world. And it comes up with what it calls as a world model, that it places all the other objects around it as it perceives, and after the localization, which is the virtual world model. And based on that virtual world model, the vehicle plans its next action based on where it's going, and then does its plan lane routing, and then figure out what the next actuation should be. And then this continues in a loop. As the actuation is done, the new sensor information comes in the next time cycle, and this process proceeds. Not so simple view is that this is usually built on a lot of system components. At the high level, it still remains the same. Like the AV still has to perceive, localize, and plan. But at the bottom level of the stack, based on how the industry, we usually have compute platform that provides the compute capability to perform a lot of this task. There is usually real-time OS, in this case, NVIDIA's Drive OS, that provides a lot of capabilities to stream data or share data between multiple accelerators or processing elements that are there. On top of it, provides a lot of building blocks called DriveWorks in this case. You can think of these as building blocks providing abstractions for capturing sensor data, sharing between different processing elements, performing I/O with the devices that you have there or the sensors you have, and the DNN frameworks, so that you can deploy a model and then you can execute it on any of the available hardware resources with different optimizations that can be performed or different optimization options you want to be enabled there, and so on. And on top of these building blocks, usually the AV system is built, which we saw in the previous slide. And also the IX, which is intelligent driver experience, that is to visualize what the car is seeing, essentially helping the passengers stay calm in some sense, because a lot of this is new technology and people need to understand what the vehicle is doing to gain confidence in it. And in case of where it is not totally autonomous, cabin monitoring will be helpful to alert the driver whether he or she is distracted, or provide them the handover. There needs to be proper handover mechanism whenever the AV, based on the stages of the autonomy, if it is not capable of driving in certain conditions, it needs to hand over to a driver, to a human driver. So with that high-level system, safety forms one of the key requirements of the autonomous vehicles. First, one of the things that has to be built into the systems is what if something goes wrong? And many things can go wrong within the system. In this example, I'm talking about mostly hardware aspects that can go wrong. One of that is maybe system design has a flaw that is uncovered much later once systems are in the field. Hardware errors can develop, permanent or transient errors that can happen due to voltage droops, high energy particles, or just degradation due to aging. And the system should be able to design to handle these situations. And more on functionality, we need to be testing our systems that they meet the desired level of autonomy. And there are a lot of research problems and challenges within this domain. And also the compute resources that are available in real-time settings are limited to a certain extent. And we want to make sure that the amount of perception, the localization, and the planning algorithms, that the resources that are required are there, or how to manage those resources efficiently so that the vehicle maintains safety. And the safety is key. At ISO 26262 and 21448, you don't need to know these numbers, but the good thing is that ISO standards give a lot of importance to a lot of the aspects that I mentioned above, and they are setting guidelines on how engineers should focus their efforts so that they quantify that the system is built to handle many of these. While the process are in place, there are still a lot of interesting research directions that still remain to be solved, and I'll be talking about some of those in this talk. So to get a little focused, I'll be talking a little bit about hardware errors. How can one go about addressing those in the context of autonomous safety? And then talk about functionality testing and close perhaps at the end on design and efficiency. So this is the outline for perhaps next 20 minutes. I'll be probably quicker on the first part on hardware resilience, spend a little bit more time on functionality testing aspect, and then with perhaps some more exploratory topic towards the end on designing efficient and safer systems as we move forward. Okay. All right. Okay, so hardware resilience. Now, ISO 26262 standard, if a system is being certified by the standard, it requires the system to be robust to single point, transient, intermittent, and permanent errors. Many of these terms may be new if you're hearing them for the first time, but people who are in this is pretty standard. But if you look at the requirements, this is ASIL A, B, C, D. This is the terminology that's often used. D being the strictest and the most desired, because that has much more strict requirements on what the hardware platform or hardware software platform has to provide. And usually ASIL D means that the fit of the device should be less than 10. That's, if you understand the numbers, that's pretty strict. That's saying like you can know the system should only tolerate 10 failures in billion hours of operation. And as you start adding many systems, these can start to add up. And that's why people don't desire the failure rate. FIT essentially stands for failure in time. So people don't desire this failure to be high enough. And so there are requirements for it to be very tight. So with this tight requirements, resilience becomes an interesting problem. Different depending on the industry you are in or your setup, different customers buy different components. For example, somebody may buy only the hardware aspect and try to build all the software aspects on their own. Some customers may want to buy the hardware and the real-time OS and perhaps the building blocks, and then they build the high-level application aspect that is connecting all the perhaps pre-trained models together to form, give a custom experience to the customers when they are building the autonomous vehicle stack. And some may want most of these components perhaps just change something at the end with some tweaks at the knob so that they just get their customization like that, but they don't have to do a lot of software development themselves. So all I'm trying to say is different customers buy different systems, and usually at the point of handoff, that's where we want the system to be robust. So, when customers always like that the requirements are taken care of by the vendors. So depending on whether the customer buys only the let's say only the hardware, then the ASIL-D requirements will likely apply just to that. If somebody is buying more system components in one package, like for example, hardware, OS, and the building blocks combined, then you have more flexibility perhaps to address all of those within that whenever the handoff takes place. So what is the problem? So first, when we started looking into this a couple of years ago, we first set off by saying, let's understand the problem. That's one of the first steps almost anybody does. So we started simulating hardware errors when we were running CNNs. We focused on CNNs primarily because a lot of the perception is performed by CNNs and in the AVs. And of course, the CNNs are widely used in many topics. And so we set out the time, we didn't have a lot of tools. So we built some tools to inject errors into the executing application. And we started off these studies by studying low-level errors and somewhat abstracted errors by looking at the convolutions. Some of the key things that we found is in CNNs, only large neuron deviations cause significant corruptions to the output. This was a very interesting insight when we found it. All it's saying is that whenever you have an original neuron value, you see a class category change or an object location change if the neuron values is significantly far from what it was originally. So we need to have a hardware error that does it. The other interesting finding was that not all feature maps within a network are equal. Some are more important than the others. We all know that even pruning techniques and all have looked into it. What was interesting is that even vulnerability was also somewhat correlated with the importance of the feature map. That is, not all feature maps need equal protection. Perhaps you can get away with some selective protection. That was one of the interesting takeaways there. And the last interesting thing is that we found that high confidence images often are less vulnerable. That was actually good news when we found this, which essentially means that if the models are trained pretty well for the data they're going to be deployed, they may be robust also. And this last study that when we did it, we looked at end-to-end AV system and we tried to understand how hardware propagate. What we found is that there is a lot of significant tolerance at different levels in the system. In this case, I was talking only about the convolution neural networks, but then there is the aggregation that's done across multiple sensors and then planning algorithms. They all add in some extra tolerance, but a lot depends on scenario dependence. It depends on the scenarios under which the AV is performing. So I'll come back to this when I talk about functional testing. There's a strong connection there, and it is important to study various driving conditions. So the previous slide was all about let's understand the space, what's going on, what can hardwares do. And in this case, this slide is basically summarizing a bunch of research that has been done in the space. Some of it is as part of our group and our collaborators, is how can you mitigate hardware errors when you're in the field? You can build in resilience into the hardware by having selective latch hardening techniques or ECC and more parity added to the DNN accelerator components, for example, or the GPUs or the CPUs, which almost always have ECC to the major storage structures. And some at the CNN level, if there is flexibility to add protection at the CNN level, simple techniques like using clipped ReLU, which is perhaps gaining traction already, can reduce a whole lot of errors, as we saw that most corruptions come from significant deviation in the neuron values. Selective protection of fmaps, that is, find out the feature maps in the model that are more vulnerable, only protect those. Maybe you get most bang for the buck that way. And recently we came up with a method of algorithmically protecting convolution. So I won't go into details, but in a nutshell, all it's trying to do is use distributive property and trying to reduce the number of multiplications that are needed only for verification, not to do the main work. And we found that with only like 6 to 20%, upwards of maximum of like 25% overhead, we can guarantee that there is no error in convolutions, which is where most of, like nearly all of the work in convolution neural networks is. At the perception stack, there are many techniques that can be done and still can be explored about selective inference protection or using the inference vulnerability information to construct the whole model that is smooth in such a manner that any glitches or temporary errors are gone, and also leverage diversity coming from sensors to make the whole things robust. Okay, so moving on to the next part, this is where I was also saying in one of the work that we did, the end-to-end study, we found that scenarios play a very important role in any kind of study we do, and is also very important for testing the system and ensuring that it is safe. So this is where we started looking at a broader aspect of safety with scenarios. So AVs need to be tested to ensure safety. Of course, simulation plays a key role to augment on-road testing. No doubt that on-road testing is really important because you can test a lot of things that perhaps simulation may not capture, or if it is not realistic enough. So the goals of scenarios is essentially to test that the AV is following the driving rules and the etiquette. It is and a lot of the scenario goals are derived from the HARA process. Excuse me for these special terms. The ISO 26262 requires the system designers to come up with a flow where they can describe a domain where the system is for which the system is being developed, do a hazard and risk analysis, and then come up with a set of safety goals. And so the goal here is to test to ensure that the AV meets those safety goals. And the next step would be more interesting thing is to understand what are the pre-crash scenarios where humans usually often stumble and teach the AVs to be safer in those environments. And the last aspect is find out all the corner cases which are really hard to navigate, but yet we want the AVs to navigate safely. Some of these can actually be intuitive for humans. For example, when information on the road lane marking is missing or something like that, we still want the AV to be driving safely. So lots of interesting problems in this and yet to be solved. So perhaps I'll focus only on one topic here and then maybe talk about a broader aspect here. So we looked at two methods to generate scenarios. The first one was we start off with, which is more intuitive. We start off with a random scenario. We pick an actor, call him or her an unsafe actor, and let them deviate slightly. So you can think of this other actor as a distracted driver watching phone or under influence of some sort and is not behaving according to the rules. And with those, we can create challenging scenarios. The other method is where we applied a genetic algorithm to find ways with the objective of minimizing the distance between the AV and any other actor, one other actor, in such a way that it's not other actor's fault. So we are interested in finding scenarios where AV can be at fault so that we can use it to test and improve the system and perhaps also do resilience studies on these scenarios. We are in this corner case. We want to make sure that the hardware errors or any other things don't affect safety under these stressed situations. So one thing after the study, what we found is generating scenarios, anybody can perhaps do that. Generating many scenarios is easy. What is challenging is how do we select most interesting scenarios from those which highlight the shortcomings of the AV stack one has so that you can improve it. So in this case, with that goal, we started looking at how can we characterize driving scenarios and so that we can down select to a smaller set, perhaps a diverse set to identify interesting problems. So our approach here, which is not, there may be other approaches, but one of the approaches we took is we discretized the space in front of the AV, looked at how the AV can navigate through that space theoretically, and we blocked off the cells where other actors are there or off the road, as you can see in this picture, as saying invalid, and then we created a tree. You can think of these green nodes as actually the nodes where the AV can theoretically go over time, where each level in the tree is the time step. And red are essentially saying the car cannot be there, you will be likely in collision. So by construction, we can see that what are the safe paths that are available for the AV theoretically. And so this is the mechanism, and then we analyzed the tree and extracted properties from it as we characterize it. So for example, we looked at how narrow can a path be? So, it is likely that to avoid a collision, you have to take a really narrow path to avoid it. That'll be a really hard scenario. And there may be some easy scenarios where like you can do almost anything and it'll be safe on the road. So these are essentially the 6 metrics. I won't go into details. Okay. So this is essentially showing the example that we were able to score or rank scenarios based on these 6 metrics that we come up with to characterize a scenario. The left one, on the left side, the first picture that you see based on the pointer is one of the easy ones, where we have an attacker coming from this side or an unsafe actor, and the AV has to simply change lane to be safe. In the other case, which is somewhat harder, is you're already taking left in that curvature. So the AV has to apply harder acceleration change to change lane to that side. And in third case, this is a synthetic, not implying that this will happen in reality, but we've tried to stress our characterization method significantly to induce a very aggressive attack to figure out how can AV stop it. And in this case, it turns out there are like very few safe options available. That is just swerve a little bit in the lane and then stop as all the other actors, the attackers go by. So the interesting thing was the tree-based algorithm was able to identify this and rank them as we expected them to be. That the first one is easier, medium, and hard. And then we applied this to do 2 data sets. First one is where we custom made our set of scenarios. And the other one is we extracted from a data set like US 101 driving, extracted from cameras posted somewhere in LA. And we were able to characterize and then extract interesting scenarios from them and even identify similar looking scenarios so that we don't have to perhaps spend a lot of simulation resources as we are testing. Okay. There are a lot of applications for the characterization work. We can use this method to generate new scenarios because we know what are the safe paths that are available. Now we can create new actors and place them to create more interesting scenarios. Using this method, we can suggest possible safe paths that can be avoided, ones that can be used to navigate safely. We can also employ that in real time if the computation is fast enough to even cross-check the paths that the original AV is taking to ensure that that is one of the safe paths that we have. But for that, we need to be really efficient. So in here, I have a lot of detailed picture here where we converted that tree-based algorithm into a tensor-based algorithm, where each tensor represents the state on the left side here of the AV, and the transition is basically when it moves to the next time step. And given that all of this is done in a tensor format, it is extremely parallelizable and can be implemented in a really fast manner, getting to almost near real time, so that you can run it in real time. Okay, so I had one more topic. So probably in interest of time, I will only talk about high-level aspects and then not go into much details here. So this is also related. Now, once we are coming up with interesting driving scenarios, we find that the perception requirements depend theoretically highly on scenarios. For example, this is two examples I tried to jot down. That is, for example, if you think of an autonomous vehicle traveling at really slow speeds on a local road, there are no obstacles and you can expect that even if you have errors or low perception quality, AV will be fine because there are hardly any safety incidents to be had. And if the AV is going through an intersection on the other case and the speeds are high, let's say you're on an expressway at an intersection, you really want your perception to be perhaps boosted to ensure that the cross traffic, somebody is not violating or about to jump a signal to perhaps make it. A lot of this is not required, but it can really help safety. So all it's trying to say is the perception requirements can be scenario dependent. And the reason I bring this up is, future systems are deploying many high-resolution cameras. This example that I took out from a recent news article that Neo Autonomous Driving System, NAD as they call it, deploys 11 8-megapixel cameras around the car, covering everything around the car twice. It employs one LiDAR system. LiDARs is relatively still expensive system that we have, so it's only one. 5 radars of 12 ultrasonics, and then other sensors also. So with this, there are new problems and challenges that emerge. That is, how much perception quality do we need? Why did they only select 8 megapixel? They probably had resource constraints. You can clearly see that once you are operating in this domain, you can keep adding more perception. But after a certain point, the amount of the returns you get for the added compute and the sensors perhaps diminishes. So perhaps this will be interesting. There are many interesting research problems in this domain to understand what is the perception quality requirement under different driving conditions, and how should we design an optimal perception stack. And the scenarios, of course, play a key role. So I'm going to zip through this next 2 slides. We did some preliminary study where we tried to vary perception parameters under some driving conditions. We tried to select hard scenarios. That is, the speeds are high, relatively high, and the AV had to apply very hard braking without any issues because of the scenario how we constructed it. And what we found is that there exists a lot of tolerance even in such hard scenarios. And in this case, we lowered the FPS. So this just probably only point to this part here, just for the interest of time, this part here, where we tried to vary FPS, or the frames per second of the single camera setup that we have. And we find that the planning algorithm was able to tolerate a lot of the degradation in perception, even in these hard scenarios. That's probably because the planning algorithm did harder braking. Even if it realized that the obstacle is there late, it had some options to avoid the collision. Of course, if you provide like really low perception output, that's not enough. Okay, so this is my last slide here, that essentially saying that a lot of research problems exist in this domain enough. And the trade-off space about how much perception is required and what kind of errors can be tolerated and how to define an efficient system is a very interesting topic. There are benefits to having multiple diversity in the sensor suite. It'll be very interesting to quantify all the benefits that we get under what conditions. And what will be more interesting is if somehow dynamic perception and boosting can be made practical. There are a lot of problems, challenges in this aspect, because the testing becomes almost like a nightmare if you have dynamic perception system. Okay. All right. So to summarize, vehicles are becoming increasingly autonomous. Safety is one of the key requirements for the AVs. And I briefly touched upon 3 topics about making systems safe by addressing hardware errors, selecting good set of scenarios for testing and for other resilience studies. And on the last part, briefly touched upon the exploratory aspect about perception being one of the compute resource demanding aspect, and designing an efficient and yet a safe system. Okay, so there are a lot of interesting research problems. I'll stop at this time.
Okay, well, thank you very much for a very exciting talk. I think we have a few questions on the chat, and then maybe we can start from there. And then if we still have time, we can then open to the audience.
Okay, right. Since I'm sharing my screen.
Yeah, so the first one's from Eric. Is Eric here? If not, then I can read it for him. Well, so he basically said airplane crashes are most often the result of multiple simultaneous problems. So is the testing of systematic faults set up to measure all of the possible combinations of simultaneous failures?
Oh, it's a great problem. I'm glad you bring it up. A lot of academia, as far as I know, have not really looked into this. As part of the system architecture, the system is designed to look at high-level aspects, high-level symptoms of failures, and there are multiple fallbacks that are being designed. There is expected, depending on the architecture of the system, there can be expected to have a hot swap available. That is another AV stack, perhaps in some degraded mode, available to operate. So once you are able to detect the system, you can fall back and then perform in some degraded mode, still in autonomous mode. Or in the worst case, if we are in level 2+ mode, you can hand over the response, hand over the capability to the human driver by alerting. That's one of the topics is you need to have proper systems in place to transfer control either to a human driver or to a backup system. But it's a good point. I think more emphasis, perhaps at least in academia, should be given on this. But at least as the systems are designed, they're looking at high-level symptoms of failures that can come up from multiple sources and can be handled.
Yeah, to just follow up on that a little bit, I guess in conventional sort of architectural resiliency world, I guess single bit flip is more often if you have multiple bits, the likelihood for multiple bits to be kind of flipped is much less likely. And so I was wondering if there is a quantification as to how often multiple system failures would happen in autonomous
I think
vehicle?
this multiple system sensor failures is perhaps not targeted mainly towards like the transient errors or particle strikes, perhaps more to do with component failures or electrical failures. For
Right.
example, the sensor is not working. And it is possible if it's raining and there is some water damage or something, you can expect multiple sensors to misbehave. Or there's other aspect about sensor blockage, that the camera is perhaps seeing mud. And if you are driving in certain environment or areas or environments, you can expect multiple of them to misbehave. Right. So
Yeah,
it
yeah.
depends on the failure mode, the type of the error you're trying to make the system robust against. Yes.
Yeah, I think once you expand from just looking at the transient error to all kinds of other sources, then
Right.
the likelihood for multiple errors to occur would increase. The next question was from me, but I guess in the interest of time, I'll just skip mine and then go to next one, Abhishek. Are you able to speak or?
Yeah, I can.
Yeah.
So my question was actually about the part where you talk about vulnerability, and so I think you mentioned a paper there. Probably I can go through that, but basically, how do you quantify the vulnerability that you talked about? How do you quantify the vulnerability of various layers? And is this quantification like limited to just the CNNs, or have you looked at other aspects of the system stack as well?
Okay. So too many slides to go back, but all right, this one. This particular graph, we only looked at the CNNs, primarily only classification-based models for this particular work and the graph that I'm showing. The graph is for ResNet 50. Vulnerability, what we call as, if you have a single neuron error, what is the likelihood that the class will change as a result of this error? And so if you think of this experiment, we conducted hundreds of these injections into the neurons in each of these feature maps that are available, and observe how often do we get a class change.
Okay.
Does that clarify? So this is only looking at those. Moving forward, we did some internal studies with different types of networks. We believe a similar aspect holds perhaps across broader class, but we don't have any. Well, it's anecdotal at this time, let's say. But more evidence would be helpful.
Okay, thank you.
Next is from Kota. Are you still there?
Yes, I'm still here.
Okay. Will you be able to?
Yeah, sure.
Ask a question. Yeah.
Yeah. So the question was whether you think that safety and resilience can be incorporated early on in the neural network design phase, or not, an afterthought. Basically, can we incorporate that as we're designing these neural networks?
Yeah, I did not touch upon that in this, but yes, there is advancements in robust models. In fact, people have been looking at to the extent of stochastic neurons, if you want to think about it, right? So there will be inherent redundancy or diversity built into the system where multiple neurons have to coordinate or provide input so that the final result is determined. And all the study that I was talking about earlier, at least here, that one neuron able to change so much, the likelihood of that will reduce. And with the use of perhaps more quantized models, the range reduces. And so a single neuron giving you really wrong value changes. And we also did some studies where we used models that are trained to guard against adversarial attacks. And so what we really wanted to see is, it'll be nice if we have a single solution for adversarial attack as well as resilience problems. And so we don't have to have different solutions for these things. Oftentimes, these are done by different set of people, and adversarial attack, a lot of that is perhaps in academia and perhaps slowly transitioning to the products. But as these are to be deployed, coming from traditional stand of view, they want to meet these requirements. One of the challenge I would say in this domain is providing solid coverage estimates. And this is where some of the other techniques I believe are lacking, that where this algorithm-based technique, I think this is one of the places where it stands out, is it can guarantee that if there is an error, it will be detected because it's making precise checksums and checking those checksums to ensure there is no error. You can make systems robust also, but we also need solid quantification under the environments where the systems are deployed to ensure that the coverage you get, that is the misses or how many escapes you get due to errors are small. So having said that, I think what you said is great. I think research in that direction would be helpful, but I think more quantification would be needed in those environments for them to become practical. At least that's my opinion.
Thank you very much.
Okay, thanks. I guess in the interest of time, we can take the rest of the questions offline. Okay,
Yeah.
Thank you very much, Shiva.